Now we discuss the motion of bodies rolling down an inclined plane. If a ball is released on a slope of inclination angle alpha with zero initial velocity, we find that the center of mass of the rolling ball performs a uniformly accelerating motion. We already saw that the distance s covered by a uniformly accelerating body during the time t is equal to its acceleration a times the square of the time t over 2. However, the acceleration a of the ball is considerably less than the component of the acceleration of gravity tangent to the slope given by the gravitational acceleration g times the sine of the inclination angle alpha. We can also perform another experiment where a solid wooden cylinder and a hollow metal cylinder of the same mass, radius and length are placed next to each other on the slope. Of the two cylinders released at the same time, the hollow cylinder rolls down the inclined plane slower than the solid cylinder, since its moment of inertia about the axis of symmetry is greater than that of the solid cylinder. Let us analyze these results quantitatively. At a given instant of time, the line of contact between a rolling cylinder and the surface of the slope is the instantaneous axis of rotation of the cylinder. Similarly, the line passing through the point of contact P between a rolling sphere and the surface of the slope such that the line is perpendicular to the direction of the motion of the center of mass C of the sphere, is also the instantaneous axis of rotation of the sphere. If a body rolling down an incline rotates about this axis through a small angle delta phi, then its center of mass C will cover the small distance delta s given by the radius r of the cylinder or the sphere times the angular displacement delta phi of the point C. The equation of motion of the body rotating about the instantaneous axis of rotation states that the moment of inertia ip of the body with respect to the instantaneous axis of rotation determined by the point P, times the second-order time derivative of the angular displacement phi of the body is equal to the z component of the torque tau produced by the gravitational force acting on the body, where the axis of rotation is chosen as the z-axis. The z component of the torque tau is equal to the weight of the body given by its mass m times the gravitational acceleration g, times the lever arm d of the weight pointing downward from the center of mass c. Here the lever arm can be written as the radius r times the sine of the inclination angle alpha of the slope. Because the infinitesimal displacement ds of the center of mass c of the body is equal to the radius r times the infinitesimal rotation angle d phi of the body, we can express the second-order time derivative of the angle phi by 1 over r, times the second-order time derivative of the displacement s. By applying the definition of acceleration, we can write the second-order time derivative of the angular displacement as the acceleration a of the center of mass c over the radius r. As a result, the equation of motion states that the moment of inertial ip times the acceleration a over the radius r, is equal to the mass m times the acceleration of gravity g times the radius r, times sine alpha. If we express the acceleration a of the center of mass c from this equation, then we obtain the ratio of the mass m times the square of the radius r to the moment of inertia ip, times sine alpha. Now we can apply the parallel axis theorem stating that the moment of inertia ip of the body about its instantaneous axis of rotation passing through the point of contact P, is equal to the moment of inertia ic of the body with respect to the parallel axis passing through the center of mass c, plus the product of its mass m and the square of its radius r. Then the acceleration a of the center of mass of a cylinder or a sphere of mass m and radius r rolling down a slope with the inclination angle alpha, is given by the ratio of the mass m times the square of the radius r to the sum of m times r squared and the moment of inertia ic, times the gravitational acceleration g times sine alpha. We already saw that the moment of inertia ic is given by 2 over 5 times the mass m times the square of the radius r in the case of a sphere with uniform density. By inserting this expression into the formula obtained for the acceleration, we can write it as 5 over 7 times the acceleration of gravity g times sine alpha for a homogeneous sphere rolling down a slope with the inclination angle alpha. Similarly, since the moment of inertia ic of a homogeneous cylinder is equal to 1 over 2 times its mass m times the square of its radius r, its acceleration on the incline is given by 2 over 3 times the gravitational acceleration g times sine alpha. We also saw that the moment of inertia ic of a hollow cylinder is equal to 1 over 2 times its mass m, times the sum of the square of its inner radius ri and the square of its outer radius r. If the wall of the hollow cylinder is thin, then the inner radius can be approximated by the outer one, which gives m times r squared for the moment of inertia. In this case, the acceleration a of the hollow cylinder while rolling down the slope is approximately equal to 1 over 2 times the gravitational acceleration g, times the sine of the inclination angle alpha of the slope. The qualitative explanation of these findings are the following. The torque exerted on a cylinder and a hollow cylinder is the same, but it will produce a smaller angular acceleration for a hollow cylinder due to its greater moment of inertia about its axis of rotation. Consequently, a hollow cylinder will roll down an incline slower than a cylinder of the same mass and radius. Now we determine the kinetic energy of a sphere rolling down an inclined plane and examine the forces accelerating the body. In the case of this type of motion, the kinetic energy of the homogeneous body of mass m consists of two parts. The first part is the energy of a point mass m concentrated in the center of the mass c of the body, where the point mass travels with the velocity v having the kinetic energy 1/2 times the mass m times the square of the velocity v. The second part gives the energy of the body rotating about its central axis, which is equal to 1/2 times the moment of inertia I of the body with respect to its central axis, times the square of its angular velocity omega. If the body rolls down the slope without sliding, then its angular velocity omega can be written as the ratio of the velocity v to the radius r of the sphere or cylinder. By substituting this expression into the second term, we are able to express the kinetic energy of a sphere of a cylinder of mass m and radius r rolling down an incline as 1/2 times the mass m, times the square of the velocity v of its center of mass, times the quantity of 1 plus the moment of inertia I of the body over the product of the mass m and the square of the radius r. Because the moment of inertia I c of the sphere with respect to its central axis is equal to 2/5 times its mass m times the square of its radius r, the kinetic energy of the rolling sphere can be written as 7/10 times m times v squared. Similarly, for a rolling cylinder with the moment of inertia I c given by 1/2 times its mass m times the square of its radius r, the kinetic energy is equal to 3/4 times m times v squared. This expression can be compared with the kinetic energy of a rolling hollow cylinder with the moment of inertia I c approximated by its mass m times the square of its radius r, which is simply equal to m times v squared. The result shows that the hollow cylinder has a greater kinetic energy than the solid cylinder of the same mass and radius if their centers of mass have the same instantaneous velocity. Now we study the forces exerted on a homogeneous sphere of mass m rolling down a slope with the inclination angle alpha. The weight of the sphere given by its mass m times the acceleration of gravity g can be decomposed into the vector sum of the tangential force Ft and the normal component Fn of the weight, pointing into the direction tangent and perpendicular to the motion of the center of mass c of the sphere. Here the magnitude of the tangential component is equal to the mass m times the gravitational acceleration g, times the sine of the inclination angle alpha of the slope, whereas the magnitude of the normal component is equal to m times g times cosine alpha. Due to the law of action and reaction, the slope exerts the force minus Fn on the sphere compensating the force Fn. We also have to take the static frictional force F sub Tf into account, acting in the direction opposite to the tangential force Ft at the point of contact P. We already proved that a system of forces can be replaced by one force applied at an arbitrary point and a force couple producing a given torque with respect to that point. Then the tangential force Ft and the frictional force F sub Tf are equivalent to their net force F sub T1 applied at the center of mass c in the tangential direction, and the force couple F sub T2 and F sub Tf that produces the torque rotating the sphere about the point c. Consequently, the magnitude of the force F sub T1 is equal to the magnitude of the tangential force Ft minus the magnitude of the frictional force F sub Tf, and this net force will produce the acceleration a of the center of mass of the sphere of mass m. As already seen, the acceleration a of a sphere of mass m rolling down a slope with the inclination angle alpha is given by 5/7 times the mass m times the gravitational acceleration g, times sine alpha, which we substitute into the right-hand side of the equation. By applying the explicit form of the tangential component of the force, we can express the frictional force F sub Tf by 2/7 times m times g times sine alpha. The angular acceleration of the sphere about its central axis is due to the torque tau produced by the frictional force F sub Tf, and its magnitude is given by the magnitude of the force F sub Tf times the radius r of the sphere, which is equal to 2/7 times the mass m times the acceleration of gravity g times sine alpha, times the radius r. After the presentation on bodies rolling down an incline, we discuss rolling friction or rolling resistance that slows down the motion of a rolling object. We saw that the acceleration a of a sphere rolling down a slope is given by 2/5 times the acceleration of gravity g times the sine of the inclination angle alpha of the slope. If a ball is rolling across the horizontal surface of a table, the inclination angle is 0 and the rolling body has no acceleration. Then we would expect that the ball performs a uniform rectilinear motion across the table and it will never stop rolling over an infinite horizontal surface. But experience shows that the rolling ball slows down and stops after covering a finite distance, due to friction and drag effects. Now we provide the quantitative description of this effect. Because of the deformation of the bodies in contact that always occurs in reality, the ball does not come into contact with the plane at one point but over a surface. The table exerts forces on the ball over the surface of contact that are greater at the point A than the forces at the point B for the direction of the rolling ball shown in the figure. As a result, the forces exerted on the ball produce a torque in the opposite direction of the rotation of the ball, reducing the angular velocity of the rotation and the velocity of the center of mass of the ball. Experience also shows that the magnitude of the torque tau with respect to the instantaneous axis of rotation of the ball is approximately proportional to the force N that presses the body against the surface. The proportionality constant denoted by the letter B is known as the coefficient of rolling friction that depends on materials and geometry. The dimension of this coefficient is length and its SI unit is meter, although millimeter is more frequently used in practice. Alternatively, the rolling resistance can also be described by the equation stating that the frictional force F sub F is directly proportional to the normal force N, where the dimensionless constant of proportionality μ is called the coefficient of rolling friction as well. The relation between the dimensionless coefficient and the one with the dimension of length can be derived from the expression stating that the magnitude of the torque tau is equal to the frictional force F sub F, times the lever arm given by the radius r of the rolling ball or sphere. If we substitute the equations expressing the torque and the frictional force in terms of the two types of coefficients of friction into this equation, we can write that the coefficient of rolling friction B as the product of the radius r and the dimensionless coefficient of rolling friction μr. Equivalently, the dimensionless coefficient of rolling friction μr is equal to the ratio of the coefficient of rolling friction B to the radius r. We can find measured data for both types of coefficients in the literature, but it might be more convenient to use the dimensionless coefficient since it does not involve any length scale. In this table we show the dimensionless coefficient of rolling friction μr for some typical cases from everyday life, starting with a rolling resistance for railroad steel wheels on steel rails, which has a very low value between 0.001 and 0.002. These figures are also the same for ball bearings. The rolling friction for bicycle tires rolling on concrete is equal to 0.002, whereas it goes up to 0.004 in the case of an asphalt road. This coefficient is already one order of magnitude greater for car tires. It is equal to 0.02 when the car is traveling on asphalt, and it increases to 0.2 or 0.4 for car tires rolling on loose sand. There are several methods to measure the coefficient of rolling friction by conducting experiments with bodies made of different materials rolling across different surfaces. For example, the coefficient of rolling friction can be determined by finding the angle of inclination alpha naught of a ramp at which a ball or sphere rolls down with a uniform velocity after a small push. The torque tau produced by the weight of the body with respect to its instantaneous axis of rotation is equal to the mass m of the body times the gravitational acceleration g, times the radius r of the body, times the sine of the angle alpha naught. The torque produced by friction is given by the product of the coefficient of rolling friction B and the magnitude of the normal force N pushing the ball against the ramp, where N can be written as the mass m times the gravitational acceleration g, times the cosine of the angle alpha naught. If the motion of the center of mass of the rolling body is uniform, the magnitude of the torque due to rolling friction must be equal to the magnitude of the torque tau. As a result, we can write that m times g times r times sine alpha naught is equal to b times m times g, times cosine alpha naught. By simplifying this equation, we can express the coefficient of rolling friction B as the radius r of the rolling body, times the tangent of the inclination angle alpha naught of the slope on which the body rolls down with a uniform velocity. Then the tangent of the angle of inclination alpha naught immediately gives the dimensionless coefficient of rolling friction μr of the ball rolling down the ramp. For a wheel of radius r rolling on the ground with a constant speed, the torque tau produced by the pulling force Fp acting in the heel hub is equal to the force Fp times the lever arm given by the radius r. Because this torque is equal to the one due to rolling friction given by the coefficient of rolling friction B times the normal force N, the force Fp can be expressed by B times the ratio of N to R, or the coefficient of rolling friction μr times the normal force N. This formula shows that the force required to drive the wheel is inversely proportional to the radius of the wheel. That is, larger wheels will generally roll over object easier than smaller ones. By applying these results, we can compare the forces that will be required to pull a car or a sledge of the same weight across asphalt. We saw that the coefficient of rolling friction μr is equal to about 0.02 for car tires in such a case. The coefficient of sliding friction μ for a sledge on dry asphalt is generally in the range of 0.7 to 0.8. Here we have the equations for the forces required to pull a car or a sledge, stating that they are equal to the coefficient of rolling friction μ times the normal force given by the weight g of the car, and the coefficient of sliding friction μ times the normal force given by the weight g of the sledge. If we divide the first equation by the second one, we can write that the ratio of the force applied on the car to the force applied on the sledge is equal to the ratio of the coefficient of rolling friction μ to the coefficient of sliding friction μ. After having substituted the values 0.02 and 0.8 into the fraction, we obtain 1/40, that is, on dry asphalt a car can be pulled by 40 times less force than a sledge of the same weight. In a car, the engine provides the torque tau necessary for smooth rolling, which corresponds to a force F acting backward at the point of contact between the wheels and the road. The magnitude of this force is given by the magnitude of the torque tau over the radius r of the wheels of the car. The reaction to this force is the sticking frictional force Fs pointing forward, which is an external force driving the car forward, provided the force F is smaller than the threshold value of the sticking frictional force Fs. Otherwise the wheels will slide instead of rolling when the force F is applied on them. This condition can be formulated by the inequality stating that the driving force F given by the ratio of the torque tau to the radius r of the wheel must be less than the maximum of the sticking frictional force Fs, where the later is equal to the coefficient of sticking friction μs times the weight g' exerted on each wheel. This inequality can also be applied for any other vehicle using wheels, such as bikes, trams or trains. In order to fulfill this condition imposed on the force F, we need a vehicle that has large weight and an engine that produces much power.